So today we're going to continue working with the product property of square roots, which we've started to learn is something that I have written in words there, something like if two or more numbers are multiplied under one square root, I can give them each their own square root and figure them out individually. What we're going to work on today in this video is what if one of those numbers being multiplied is a variable like x to the third power. So the first thing we're going to talk about is how would we take a square root of a variable. Now the most important thing to remember is any variable with an even exponent is going to be a perfect square. So for example, the square root symbol itself, that thing right there, is leading us to think about a sentence in our head. What times itself 2 times is a certain number. So for example, if I asked you the square root of 16, that is 4, because if I took 4 and multiplied itself by itself 2 times, I would get the number under the square root. Another helpful way to think about square roots is draw a picture, and that's what I have down here. So if I ask myself, for instance, with numbers first, like what is the square root of 36? I'd be asking myself, what would I put in each of these boxes that are the same, and if I multiplied them together, I would get 36. Well, that's why the square root of 36 is equal to 6, because I would put a 6 in each of these boxes. So when we start to transition to variables, anything with an even exponent will be something that we would be able to figure out by hand. So for instance, if I was asking myself, what is the square root of x to the fourth? In other words, what would I put in both of these boxes that after I multiplied them, I would get x to the fourth? Well, that would be x squared, because x times x times x times x would give me x multiplied 4 times. So the square root of that is x squared. If I ask myself, what is the square root of x to the 10th? I'd be figuring out how many x's would I put in each box, knowing that they have to be the same, to get 10 x's multiplied together in the end. Well, I would put 5, and I would put 5. One last time, if I ask myself the square root of x to the 20th, how many x's would go in each group that are the same to get 20 at the end? Well, I would put 10 in each box. So the square root of x to the 20th is x to the 10. So if it's even, we can split it into 2 equal groups. If that number is not even, like x to the 11th, we will not be able to calculate the square root directly. Because if I asked you how many x's would you put in each of the boxes, and they have to be the same to get x to the 11th, well, I can't take 11 x's and split them evenly into 2 groups. It just won't work. I could put 6 here and 5 there, but it's not the same in each box. So summarizing, we only know the square root of a variable if it has an even exponent. So if we know it is a perfect square with an even exponent, if a variable has an odd exponent, it is not a perfect square. Just like we saw before, the square root of x to the 11th was not something that I could do in my head, whereas the square root of x to the 12th is something I can do. So if it's odd, what do we do? Well, to help you, to simplify any non-perfect square variable, we always split it up in the same way. The biggest even number before 11 would be 10. The biggest even number before 15 would be 14. So what we do is we take all of the x's, which are an odd number, we put 1 in the first group, and we take 1 away after that. So for instance, if I was simplifying the square root of x to the 15th, I would split it, or I'd rewrite it as x to the first power times x to the 14th power. Because again, if 2 things are being multiplied under one square root, I can split them each into their own. So by splitting them each into their own square root, one of them is now an even exponent. What times itself twice would be x to the 14th? Well, that would be x to the 7th. And our last really important rule when we're simplifying odd exponents for perfect squares is that any variable that has the first power under a radical is in the most simple form. We can't break that down anymore. So this has a variable to the first power. We will never know what the square root of x is because we don't know what x is. So my final answer then would always contain a variable under a radical to the first power. So summarizing that process, if we're trying to simplify a non-perfect square, we want you to treat it the same way as you would with numbers. So what I mean by that, if I was simplifying something like 48, which is not a perfect square, the first thing I have to do is rewrite that number as a product of two other numbers. But what we want is we want one of the numbers to be the biggest perfect square possible. So if I was going to think about 48, should I use 4 and 12 or should I use 16 and 3? Well, I want to use 16 and 3 because that's the biggest perfect square. So if I have the biggest perfect square, I can split them up into two individual squares, and then I get the simplified form of 4 times root 3. The same exact thing is going to happen with our variables. We are going to take the exponent, that's not a perfect square, and we're going to rewrite it as a product of two other variables of the same base. But just like over here, when we did it with numbers, one of those factors must be the biggest perfect square possible. And we remind ourselves that the biggest perfect square that goes into an odd exponent is just the even number that's right before it. So what I mean by that, instead of x to the 11th, I could write that as x to the 1st times x to the 10th. Because if I split them into their own square roots, I know how to evaluate the square root of a variable with an even exponent. What times itself twice would be x to the 10th. This would be x to the 5th power. As we wrote down before, the square root of x will never simplify. Just like over here, how the square root of 3 would never simplify because there's no perfect squares that go into 3. There is no perfect square that goes into x. In other words, I can't rewrite x as x times something with an even power. It just wouldn't work. So I am done at that stage. So this is an example of like a full type of exercise that you would do in this unit with numbers and variables. So whenever we're trying to simplify radical expressions that have numbers and variables, this is what we're going to do. So I have a reminder of what it means to simplify. I have our perfect square numbers here just as a reference. And I put a little picture here to remind us that variables are perfect squares if they have an even exponent. So according to our list of steps here, what I want us to see is under that square root, we have 48 times x to the 17th. If two things are being multiplied under one square root, we should break them up into separate square roots. And as it says up here in the directions, we want to split them into numbers and variables. So I'm going to give 48 its own square root, and then x to the 17 would get its own square root. So we've separated it into two smaller problems, so we can just simplify each one on its own. So like the square root of 48, I would rewrite that as 16 times 3 because it's not a perfect square. The same thing with x to the 17th. That is not a perfect square, and as we did before, we could rewrite that as x to the 1st times x to the 16th. Now over here, if two numbers are multiplied under one square root, I'm going to give them each their own square root. Same thing over here. If two things are multiplied under one square root, I'm going to give them each their own square root. And then we can simplify the perfect squares. Like this is a 4. That number won't simplify. Any variable to the first power under a radical won't simplify. We wrote that down before. And what times itself twice would have given me x to the 16th? Well, that must have been x to the 8th. So this is x to the 8th. Now, as a final reminder as how to write our answer, what I want us to remember is these rules. The way that we simplify our answer, or how we write our answer, is we're going to put all the numbers without radicals first. So that is a 4. The next thing we're going to do is we are going to put variables without radicals second in alphabetical order. Well, there's only one, so that's going to come next. That's x to the 8th. And then any square roots that cannot be simplified, so instead of writing the square root of 3 times the square root of x, we should just join those back into one square root and do the reverse of that property, because the idea is, why would I want to have this square root that I don't know and this square root that I don't know? Why don't I just simplify it into one square root that I don't know? So this would be the best way to write your final answer. Now you might be asking, like, how do I know if I'm right? That's a big problem. So again, we just thought that we simplified this problem into that. So how would we check? Well, by definition, we said that if we took 4x to the 8th and multiplied it by itself twice, I should get the original thing under the square root. So let's check to see if that happens. We can rearrange. Let's put all the numbers first. So I'll put the 4 and then that 4. Then we have x to the 8th, and then we have x to the 8th. So I'm just rearranging. And then we have root 3x and root 3x. So if we keep going, 4 times 4 is 16. 8x is being multiplied and 8 more x is being multiplied. Would be 16 of those. Now what I want us to see here, if I have two separate square roots, I could join them back together into one square root. Now there's two ways we can see this. I can multiply those together to get 9x squared. And if two things are being multiplied, I can split them all into their own square roots. And the good thing for us is both of those are perfect squares. So out of 16, x to the 16th, this turns into a 3, and this turns into an x. So if I rearrange again, I get 16 times 3 times x to the 16th times x, which is 48 x to the 17th, which is exactly what we originally had under the radical. The last way you could see this as a shortcut, once I'm here, if I had 16x to the 16th, when I look here, I'm asking myself, what would I multiply twice to get this? Well, obviously that's just 3x in every box then. So I could get 16x to the 16th times 3x, which is still 48x to the 17th. So do one more example here. We're simplifying radical expressions with numbers and variables. So as we know from before, the first thing we are going to do is split each number and letter into its own radical. Because if they're all being multiplied together up here, let's just split them all into their own square root sign. So root 12 times root x squared times root y to the 5th times root z to the 7th. We're just going to simplify each one. So instead of 12, we can call that root 4 times root 3, which is root 4 times root 3, which is 2 root 3. This one, it's an even exponent, so I already know the square root of x squared. That's just x. When I look at y to the 5th and I see that odd exponent, I need to rewrite it as y to the 1st times y to the 4th. And then if two y's are being multiplied under one square root, I can give them each their own square root. And y to the 4th is now a perfect square. What times itself twice would be y to the 4th? Well, that's y squared. And I'm going to keep the square root of y because it has a power of 1. We're going to do the same exact thing with z to the 7th power. And z to the 7th power, again, has an odd exponent. So we're going to split that into z to the 1st times z to the 6th. And if two z's are being multiplied under one radical, I can give them each their own radical. And since z to the 6th has an even exponent, I know its square root is z to the 3rd. And then the square root of z is never going to simplify. So to simplify my answer and write it in the correct form at the end, we're going to put the numbers first. So that'd be a 2. Then we're going to put all the variables without radicals in alphabetical order. So the x would go next. Then we have a y squared. Then we have a z to the 3rd. Then we put all the radicals that didn't simplify at the end. But all the radicals that don't simplify at the end can be combined back into one radical. So this would be our final answer on this problem.